Hi, I'm Luke McKinney, Prep 101's ENGSCI 1022 instructor. In previous videos we saw forces and moments. Now we see how to answer the specific question, finding the equivalent force and moment at a location, or the equivalent force and its location on a body to create that moment.
Now that we've got forces and moments, it's time to look at equivalent forces, equivalent moments, and their locations. Now, what are those? Well, the idea of equivalent forces and moments is if we have some structure with some forces and moments acting on it, we could be asked to find the equivalent force and moment at some point. So let's say if we wanted the equivalent force and moment at point A, we would calculate what is the total force and moment there that would do the same thing. Or we could be asked for the equivalent force and its location. In that case, we take it and we have an equivalent force, and now you see we've moved it out some distance from the pivot so that it'll generate the moment for us. So it's a way of simplifying a situation. Like if you're building a bridge and there's 100 different forces and moments acting on it, and you want to work out what the support needs to deal with. You don't want to go through all the 100 bits and pieces. You just want to work out the equivalent big number and then work out how to support that. So how do we calculate them? Well, they're pretty nice. To find the equivalent force and moment, the equivalent force, sometimes called the net or total force, is just the sum of all the forces. As usual, forces don't really care where things are. The equivalent moment around a point is the sum of all the moments around that point. As always with moments, you need to specify your pivot, because if you used a different pivot, you'd get a different answer because there would be a different total moment around that point. Now, what about location? You're not always asked for this, but sometimes you are. So if you want the location, first you do the equivalent steps. You find the equivalent force and the equivalent moment around the origin. And you can set the origin wherever you want. We'll do a little example of that in a moment. And then the equations for that is the equivalent or total moment around the origin is equal to the y component of the equivalent force times the x-axis intercept and the total equivalent moment around the origin is equal to minus the equivalent force x-axis y-intercept. Now, the first thing you say when you look at that is, why is that one negative? And now you'll always remember it. Why is that one negative? The y-intercept is negative. Now, what does all this intercept and equivalent mean? What it means is when you've got your origin, your x-axis and your y-axis, and you've worked out your equivalent force and its location, your big equivalent force will have some line of action telling you where it is. Now we can see here's where it intercepts the x-axis, and here's where it intercepts the y-axis, which is a lovely little sketch, but a sketch isn't what you have to do as an engineer. What you have to do is examples and problems and all of that stuff. So let's do a couple of those right now. So we've got a beam with a bunch of loads on it, forces and moments, and we're asked what is the equivalent force and moment at A, and what is the equivalent force and its location on the line AB. And then a little tip, take the origin about A, which we would do anyway because the first part had already told us to work things about that. So let's do the first part first. What is the equivalent force and moment at A? Well, the equivalent force is just the sum of all the forces, and that has x components and y components. So the sum of all the horizontal forces is 0. That's handy. If something's 0, you don't ignore it, you do it and say it's 0. Then the sum of all the vertical forces is minus 30 down, minus 10 down. So that's minus 40 newtons down. And remember, forces don't care about point moments. That 15 Newton meters doesn't do anything to this. Then we take the equivalent moment around A, is the sum of all the moments around A. So we have 30 newtons, a perpendicular distance of 2 away, and we see that's turning clockwise. And this reminds us, oh yeah, shouldn't be careless. I should draw my little axis so I remember which way is which. And we see the 30 newtons will rotate it clockwise around A, which is negative. Then we have the 15 Newton meters, the next part, and that's already a moment. So you don't multiply it by anything. Remember, it's force by distance, but a moment is already a moment. Sounds very romantic, but it's engineering instead, the opposite of romance. So that's counterclockwise, which is positive, and then 10 meters, the full distance of 5 meters away, and that would turn clockwise around A, which is negative. And so we find the total moment around A is minus 95 Newton meters. So that's the equivalent force and moment. And in fact, if we wanted to redraw this beam, let's say we were building an embedded support, we wanted to shove A into the wall. It's a 5 meter long beam. And in terms of A, we can now say, okay, that's 40 newtons down and minus 95 Newton meters. So that's 95 Newton meters clockwise at A. Now that we've got that, we can move on to the second part of the problem. What is the equivalent force and its location on the line AB? Take the origin about A. So they won't always tell you to do that, but that's the method. So we've got A now is the origin, x-axis, y-axis. We want to find on the line AB, which we see now is our x-axis. So we're looking for the x-axis intercept. So the total moment around the origin is the total equivalent force, y component, times the x-intercept. And we have those already, which is nice. So minus 95 Newton meters is equal to minus 40 x-intercept. So the x-intercept is 2.375 meters. And that makes sense. If we draw it, we can see we had a beam with an equivalent force and moment, 40 newtons, 95 Newton meters. You can see I redrew that. That helps a lot, especially when you're practicing. If you try to do 3 things on the same diagram, you end up getting none of them done. But for the moment around A, that's the same as 40 newtons at distance of 2.375 meters away, because you can see that'll create the same 95 Newton meter moment. Let's do a bigger example. We've got a bent member, AOB, with some forces and moment on it. What is the equivalent force on AOB and its intercepts with the x and y axes? So this time they've explicitly asked for the intercepts, but we do it the same as we do it before. We find the equivalent moments around the origin, the equivalent forces, and then we use the equation to find the intercepts. So the first step, the equivalent force, x component, is just adding up all the horizontal components, which is minus 20 Newton. Likewise, the equivalent force y component, we just add up all the y components of the force, which is minus 40 Newton. So now we have our equivalent force. And in fact, if we wanted to draw it, we can see it's minus 20 to the left and minus 40 down. So it's going to be diagonally down and to the left. We could calculate the angle if we wanted to, but we don't need it. We already have the components. So now let's take the equivalent moment around the origin. because we're going to need that for our calculations. So that's the sum of all the moments around the pivot of the origin, which is, we have 20 newtons, a perpendicular distance of 3 meters away, and that would be turning counterclockwise around the pivot, which is positive. Then we have 50 newton meters right there. That's a moment. A moment is a moment. It has no distance. Ah, the romance. So we don't need to multiply that by anything, and that's clockwise, which is negative. Then we have 40 newtons, a perpendicular distance of 7, and we see that would rotate things clockwise around O, which is negative. So we add all those up, we have minus 270 newton meters around the pivot origin. If we were asked for the equivalent force and moment at the origin, that's all we'd have to do. But we're asked for the x and y intercepts. So we do the final step. The equivalent moment around the origin is the equivalent force y component times the x intercept. So that's minus 270 is equal to minus 40 times the x-intercept. So the x-intercept is 6.75 meters. Then the equivalent moment around the origin, y is this one negative. So the y-intercept is negative. So we've minus 270 is equal to minus 20 times the y-intercept. Haha, almost forgot it there, you see. Always read the formula correctly. This is the minus, but you can see you need to have that minus there as well. This is why I always put my numbers in brackets, you see. Just assuming that you'll remember minus, or worse, trying to do stuff like minus times minus is plus in your head, always eventually leads to disaster, usually at the worst time, like when you're stressed in a big problem in the exam. So always do things one step at a time. So we have minus 270 is equal to plus 20 times y-intercept. So the y-intercept there is actually minus 13.5 meters. So what does that look like? Let's have a look. What this means is the x-intercept of our force is at 6.75 meters in the x-axis. And we already know it's tilting down like that. And it intercepts the y-axis at minus 13.5 meters. And we can see, oh, that's just trigonometry. That's the line of action of that force. So we could have worked it out with trigonometry as well. But honestly, doing it with the formula is much quicker and easier. We also see this means the intercept doesn't actually have to be part of the structure. It's just something we work out.
I hope that was useful. There's plenty more videos in the playlist, but what's even more useful is lots of exam examples and exam specific advice. And that's what we do in the prep sessions. So join the Prep 101 Study Hub Facebook page to find out when those go on, and many of them are even free, so you definitely don't want to miss those. Hope to see you there.